Okay, let's begin with Sn1 and Sn2 reactions. So an Sn1 reaction is a reaction that occurs in two steps. The first step is the formation of a carbocation. The second step is a nucleophilic attack. An Sn2 reaction is a one-step reaction, which occurs by a nucleophilic attack and an expulsion of the leaving group within one step. So we'll touch on those in our examples. So let's begin with the Sn1 mechanism and some of the properties of Sn1 reactions. Sn1 reactions typically occur in the presence of weak nucleophiles. So if you see something like water, it's going to be more likely to be Sn1, but it's not definitive. Another criteria for an Sn1 reaction is having a substituted carbon where the leaving group is. So things like tertiary carbons and quaternary carbons are more likely to undergo Sn1 mechanisms because they can make stable cations. Another case is having a resonance stabilized cation, which will favor an Sn1 mechanism. So those are some of the three cases in which you can get your Sn1 mechanism. So let's have a look. So here we have water, which is a weak nucleophile. The second thing we have is a resonance stabilized cation. So what's going on? This double bond can move here and stabilize the cation that forms on the carbon which contains the leaving group. Remember, the cation forms on the carbon with the leaving group because once the leaving group has left, it forms the cation. That is the first step of an Sn1 mechanism. So I've illustrated that step here. First, the leaving group is going to go. Then you get your cation. Then this double bond is going to move and stabilize that cation. And so what you get is this. You get the cation existing here and here in these two resonance forms. Because remember, the double bond is going to donate electron density to this carbon, which is electron deficient. Now, what's going to be the major product of this reaction? Because if you have two cations, surely you can get two products. The major product will be the cation here, because this resonance form, this one right here, is more stable than this resonance form. The reason is that this resonance form is a secondary cation, whereas this is a primary cation. Secondary cations are much more stable than primary cations. So, the leaving group has left, we've generated our cation, and this water molecule is going to come and go in and do the nucleophilic attack at this position. And we get our products. Now, why did I say products and not product? That is because this carbon here is chiral. So when we go through our Sn1 mechanism, we get a racemic mixture. We get the R and the S enantiomer. Now, why do we get R and S? Carbocations, if we were to just draw one here, are flat. They're known as sp2, hybridized carbons. What that means is that because it is flat, an attack can occur from here, like from beneath, or from above. And when something can attack from two different positions, it can generate two different enantiomers. So if we look at this example, let's go through the steps. First, we generate the cation. So this is an Sn1. So the leaving group leaves. Expel the leaving group, there's our cation. Then the nucleophile is going to and attack, and we generate our racemic mixture with the dash and the wedge. Next, let's move to an Sn2 mechanism. So in an Sn2 mechanism, it occurs in a single step. First, we expel the bromine. Once the bromine has been expelled, we get the nucleophilic attack occurring at the same time. So you draw an arrow, expelling the leaving group, and the nucleophile attacking at the same time to generate your product. Pretty simple, right? Same thing here, except this time we have a chiral starting material. On the MCAT, whenever you have a chiral starting material, and it's an Sn2 mechanism, you're going to generate the enantiomer. Well, not the enantiomer, but the opposite configuration. So, first of all, we get the attack, and then it flips the stereochemistry at that position, and you get this configuration, where that NH2 has now on a wedge instead of a dash, like the Cl. So that's the Sn2 mechanism. It occurs in one step, where the leaving group is expelled at the same time the nucleophile attacks. And notice, the nucleophile is doing an attack from the back, or a backside attack. That is why we get the opposite stereochemistry. So if we were to look at this from another perspective, so let me just redraw this in a perspective that might assist your understanding. Just for convenience sake, I'm flipping this to a wedge. So just to make it more clear, it doesn't matter at the end of the day, but I'm just doing this for illustration. Okay, so here is our perspective. We have the chlorine coming right towards us. We have a hydrogen in the back. We're doing the Sn2 attack. So the NH2 in the Sn2 mechanism attacks from the back, which means it makes a bond on the opposite side to which the leaving group is on. That's what we mean when we say backside attack. So it's coming from the dash side, not the wedge side. It doesn't do this, like that. That doesn't happen. It's coming from the back. And so when it does that, it's going to expel this chlorine. And because it is attacking from the back, you get this. So that is a very key component of an Sn2 mechanism, and it's the reason we generate the opposite configuration. The last mechanism is an E2 mechanism. So what's an E2? An E2 reaction is when you use a strong base. Now, what's a strong base? So these examples of strong bases are OH minus, NH2 minus, and a variety of others. Essentially, oxygen and nitrogen tend to be quite strong bases. And so, if something is a strong base, it can behave as a nucleophile and as a base. And so one mechanism that can happen is the following. Our strong base can grab a hydrogen from the carbon that is adjacent to the leaving group. So if you call this position 1, this is position 2. And when it does that, the electrons from that bond to hydrogen come and make a double bond and expel the leaving group, and you get an alkene. So this mechanism can also occur. And so the steps in the E2 reaction is deprotonation. This is all in one step, by the way, but I'm just putting them as separate steps for illustration purposes. Deprotonation, double bond formation, and leaving group expulsion. So that's how you do an E2 mechanism. So we've covered SN1, SN2, and E2. Let's talk about other reactions on the MCAT. Now the thing is with the MCAT is it's not mechanistically heavy. It's important to just know reactants and products as well. So let's talk about oxidation of alcohols. This primary alcohol in the presence of PCC has become an aldehyde. This is the first thing that you want to know about when it comes to oxidation of alcohols. Now, another reagent we can use to oxidize alcohols is Jones reagent, which is sodium chromate. And it's an acidified solution. So in the presence of these, what we get is this. We get the oxidation of a secondary alcohol into a ketone. Now, what about a primary alcohol with Jones reagent? What do you think the product is? Well, the product is actually a carboxylic acid. So Jones reagent can turn primary alcohols into carboxylic acids. Tertiary alcohols are generally not oxidized any further. So, those are oxidation of alcohols. Let's do a couple of examples here together. So, let's begin with this alcohol. Let's treat it first with PCC. What product do we get? So, we have this alcohol. It's a primary alcohol. And we've oxidized it with PCC. And we have formed an aldehyde. Then we do it with Jones reagent. We get the carboxylic acid. Let's do a secondary alcohol. So, if we treat a secondary alcohol with Jones reagent, what do we get? You get a ketone. So that is how we can think about the oxidation of alcohols on the MCAT. Strong oxidizing agents include Jones and also KMNO4. PCC is a weaker reagent in terms of oxidizing than Jones. Now, for tertiary alcohols, we said that they don't really get oxidized. The reason is because there is a lack the carbon-hydrogen bonds. Without them, oxidation is not going to take place. So, let's have a look at another reaction. Let's look at reduction of ketones and aldehydes. So what do you think the product of this reaction is? Pause the video and see if you can think of it. If you treat a ketone with lithium aluminum hydride, you can generate an alcohol. If you treat the ketone with sodium borohydride, you can generate an alcohol. This occurs in every case. You can generate the alcohol from a ketone through this mechanism. So let's look at the differences between sodium borohydride and lithium aluminum hydride. So let's have an ester and add lithium aluminum hydride. What's going to happen? So, if we add lithium aluminum hydride to the ester, we're going to get reduction. And we get the reduction reaction that occurs. And we are going to make that ester into what? Pause the video and see what happens. I'll give you a few seconds to come up with an answer. When you treat it with lithium aluminum hydride, what you get is the following. And this. You get these two products. Now, if we wanted to just draw and think of a fast way to draw the product, when you treat an ester with lithium aluminum hydride, I'm doing O, R, and R prime, you're going to get the following products, which are R, OH, R prime, OH. Sodium borohydride cannot reduce esters. And that's a key thing to bear in mind, especially for your MCAT. So, hopefully, that helps in your understanding of the reactions of sodium borohydride and lithium aluminum hydride with esters. So, let's look at some more examples. What about carboxylic acids? What if we add sodium borohydride to a carboxylic acid? You get no reaction. If you add lithium aluminum hydride to a carboxylic acid, what do you get? We get this. You get two products. Sorry, not those two products. You get these products. This is your product. We have reduced a carboxylic acid to a primary alcohol. Sorry, just one product. The other reagent that I was thinking about was dibol with an ester, so I flipped the two. But these are our reactions with carboxylic acids. No reaction with sodium borohydride, and we get a reaction with lithium aluminum hydride. So let's try another example. See if you can draw the product of this reaction. if we add lithium aluminum hydride, we will get our product here. You can always check the number of carbons, 1, 2, 3, 4. You get 1, 2, 3, 4. In none of these reactions are you adding any carbons, so make sure in your product that that is indeed the case, that you haven't accidentally added any carbons. Okay, so sodium borohydride and lithium aluminum hydride work differently to each other. So let's do a summary. Sodium borohydride can turn aldehydes to primary alcohols, ketones to secondary alcohols, it's inert to most other things. Lithium aluminum hydride can do aldehydes to primary alcohols, ketones to secondary alcohols, carboxylic acids to primary alcohols, and it can do esters to alcohols. It can also do a couple of other functions, which is it can turn nitriles and amides to amines. And we'll go through an example. So, let's do lithium aluminum hydride and an amide. So, let's take this amide. Let's add lithium aluminum hydride. And our product is this amine here. Lithium aluminum hydride can also work with nitriles. So let's have a look at the product there. So if you have a nitrile and you add lithium aluminum hydride, what are you going to get? You're going to get a primary amine. Why is it primary? Because you started with one carbon, you'll end with one carbon. In this case as well, you get a primary amine. That's because this nitrogen is just simply bonded to two hydrogens. If we had another case, which is where we had this, and we had a CH3 group here, like that, then you would get a secondary amine. So, this is the use of lithium aluminum hydride. So, lithium aluminum hydride, because sodium borohydride is quite simple, just ketones and aldehydes, carboxylic acids, amides, nitriles, esters, ketones, aldehydes. It's a pretty strong reducing agent. So these are things that you should remember. Okay. Next, let's go through another reaction on the MCAT. NAS, nucleophilic acyl substitution. So, the key is in the name. This is what we got going on. Carboxylic acid derivatives, like the acid chloride, can undergo NAS reactions. So, let's say we have ammonia, for example. What's going to happen here? So it's going to go and do the attack. You form your tetrahedral intermediate. Get the formation of the bond. The double bond forms again and kicks off the Cl. That should not say Cl minus, it will just be a Cl. It'll become a Cl minus once it goes into solution. Now, that Cl minus there can go and grab the proton from here, and we get our amide. That's an example of a nucleophilic acyl substitution. There's many ways that this can happen to generate a variety of products. They kind of all follow the same mechanism, and it is fairly straightforward, so I won't spend too much time on them. Just know that you form a tetrahedral intermediate, and then you get the expulsion of the leaving group, and that's just kind of how it happens. So, the next one is hemiacetal and ketals. So let's think about this. So what's a hemiacetal? So if we add an acid to this, this thing will come and grab the proton, and we end up with this structure here. This is known as an activated carbonyl. That because it is very electrophilic. The reason it's so electrophilic is because there is the ability of a molecule, so sorry, that should say R, it's an alcohol, that is more likely to attack now because it is protonated. And so we get the attack here. So we end up here. Now, this is now positively charged, and it's going to lose that proton. And so, we end up here. This is our hemiacetal. So I'll pause the video there, and our next lecture will continue our organic chemistry discussion.